Alrighty, let's get started. Hello, everybody. Thank you for coming. Happy Thursday. Uh, yeah, happy Thursday.
You got some people on Zoom with us today?
Yeah, Renway's on Zoom. Um, okay, so today, marks we're one class period closer to the final exam. Um, so today we're talking about algorithms. Maybe we'll get to sorting, maybe not, we'll see. Um, Next Tuesday, we'll definitely be working on sorting. Next Thursday, depending on how fast we go, we may have a lab that day. And I'll try and have the study guide for the final up for you. So this is next week. Then the week after that, Thanksgiving. And then the week after that, the first week of December, we'll look at trees, binary search trees, which is not on the final. And then we'll look at the Thursday, it'll be final exam day or review day. And then final exam will be Thursday the 12th at 1 o'clock. Okay, just to remind you, here's where we're at. The other thing I need to tell you, homework 2 is due next Friday, which is 1 week and 1 day from today. So as of tomorrow, you have a week left to do it. So make sure that you're meeting with your groups and that you're working on it. Send me an email if you run into problems. Okay? It's your responsibility. If you haven't started it, get going. Please do not wait until the last minute. That's a pain for you and for me. So start early, fail early, and then you can fix it. So today, the plan for today is we're going to learn about how can we say an algorithm is efficient. We're going to do kind of the hand wavy explanation, but it gets us going. We'll have a worksheet that I believe I've printed enough. And so that'll be our active learning for today. And then we'll see where we are. Maybe we'll start sorting. Okay. So, so far we've looked at creating data structures. That's what we have been doing in this class. So we start off with what's Java? How do you print something? How do you do math? And then we looked at the inheritance, the object-oriented part of Java. And then we started looking at data structures. So using our skills to build data structures. And so once we've got the data structures, the things we can do with them are called algorithms. And so we've developed some algorithms of our own. We have some recursive algorithms that we just did. Some of the linked list operations that we made, those are algorithms in and of themselves, where an algorithm is basically, an algorithm is like a recipe, right? Where it says, here are all your ingredients, follow each step and do this until you've done all the steps and then you're done. That's an algorithm. So, yeah, so when we've got our algorithms, so these programs that do something, we need a way to measure how good it is. So one step is coming up with the algorithm to say, here's what I want to do. The other step is to say, well, how good is it at what it's doing? And so we use something called algorithm analysis to check that. We're looking at its efficiency of how well it's doing. And so the two things that we really care about when evaluating an algorithm are space and time. And so space is how much it, like how many variables it uses up in memory, like how much space, how many variables and stuff does it need to do the calculations that we need it to do. And then time is how long it takes. So we've seen that some algorithms are faster than others. So like for our Fibonacci, when we did Fibonacci of one through 5, it's quick, right? It gets done right away. But when we give it Fib of 50, when we haven't done the memoization, it takes longer. If we give it fib of 100, it'll take even longer. And so we've seen that some algorithms are faster than others. And so we want to know, how do we measure that? The thing to know is that we don't necessarily count it in the number of seconds. So even though in programming languages and certainly in Java, there's like a timer function where we can like start the timer, run this, stop the timer, report how good it did. That's going to be different depending on the machine that you're using. So like if you've got this really, really old laptop, like a laptop from 2005, and you run something on it, chances are it's going to take a long time, right? As opposed to if I've got a supercomputer and I send this program to the supercomputer, it's going to happen in like no time at all. It's going to just be done. So even though it's doing the same program, it's going to take a different amount of time for those two machines. So stopwatch time isn't necessarily what we want to use for this. We want to have like a higher level of evaluating what's the efficiency of this program. So the way we do that is with something called big O notation. Big O notation is saying how many steps is this going to take in the worst case. So there's other big notations. There's like big theta, big, I don't remember the other ones off the top of my head. I'll get there. But there's other things that measure like the best case or the average case for how an algorithm performs. Big O is the worst case. So in the worst case, like if I give you like, so because sometimes it depends on, like if you're looking for something and if you start at the beginning and you go element by element and ask, is it here? Is it here? Is it here? Is it here? So the best case is that it's the first thing in the list, right? So if you're looking through a list and it's the first thing, great. You've only done one comparison. But if it's at the end, then that's the worst case. So like the worst case is that you have to compare, you have to check every item as you go, and then you eventually find it at the end. So big O is the worst case complexity. And it is what we call computational complexity. So instead of like having a stopwatch or a timer, we're calculating the computational complexity. The way that we do that is we have to choose a main operation or a series of operations and say, what's the most important thing that this code is doing? And then how many times does that thing happen? Yeah, so some really good candidates for operations to choose are like assignments. So if there's an equal sign or addition, that may be a good operation. For our linked list, something like get next might be an operation because that's doing something. And then if we're iterating through a list, we would do that thing as many times as things are in the list, right? So the operation that we choose can vary depending on the algorithm that we're looking at. It doesn't always have to be addition or some math. So the easy way to get the big O notation is to look at how many loops do we have. Let's see, do I have hold on, do I have an easy one on here? Kind of. Okay, let's look at okay, let's say we have a loop And let's say up above the loop, we have like int x equals 0. And then, so we're going from I equals 0 up till I equals n. And so at each step, we say x plus equals I. Word auto capitalizes it, but you get the idea. And so I would say this is a good candidate for assignment or for the operation. And so we count how many times did this happen? So how many times do you think it'll happen? So what if n is 5? If n is 5, it'll happen 5 times, right? Because we'll go 0, 1, 2, 3, 4. If n is 10, it'll happen 10 times. So we generalize it to the size of the input. So whatever n is, we'll say this operation is happening n times. And so with that, we can say that this function is, or not O of 1, O of n, right? So however many times it happens, we stick that in the parentheses. So we say big O, so capital O. When you write it, sometimes you draw like the little swoosh through the O, like that. And then in parentheses, you say, here's the worst case in terms of the input. So we assume n is the size of the input. Okay. So yeah, so the easy way is to count the number of loops. So like for that function, it just has like one for loop. And so it's got one for loop. Excuse me. We have to make sure to look at the arguments. So like we have to look at this and see, are we going from 0 to n? Because maybe we're not doing that. Maybe we're doing something different. So make sure to look at that. The other thing is, I have ignore constants here. So this, if we're looking at assignments, right? This is an assignment. This is an assignment. This is an assignment. When we're looking at worst case complexity, we tend to ignore all the incidental things. So if we were actually going to say how many assignments happen in this code, it would be what? So there's one here at the beginning, plus n of these happening. And then n of these happening. And so this is the whole equation of like, these are all the steps that we're taking in this algorithm. When we're doing big O, we kind of get to take what we need and throw away the rest. So we've got a 1 here, throw it away, ignore it. That's a constant. Even if there were like 500 of these lines, it would still just be like 500. And that's a constant, throw it away. The other thing is we've got n plus n. And so when we do that, we just pick one of them and throw the other one away. So that way we've just got O of n. So the sneaky way to do this is to look for the biggest power of n, keep that, throw away everything else. If we had this for loop 500 times, so like if we had 4, 4, 4, 4, 4, then it would be something like this. We would still choose only one of them, throw away the constant in front of it. It would still be O of n. Yeah, so ignore constants, round up if you need to, because we're interested in the worst case. So some of the common complexities that you see are O of 1, which we call constant time, O of n, which is linear, n squared is quadratic, n cubed is cubic, so you can also just say n cubed. The other common ones are like log n and n log n. So I should have, I have a slide later about logs. But this is a chart of like, so we can classify pretty much every algorithm and say, here's how good it is. Here's what the complexity is. And then from that, we can say how good it is. So the fastest ones tend to be log n and constant time. So those are down here in the green, which take almost no time at all. N linear time, it's okay. N log n is a little bit worse. It's the rate of increase is higher, but it's still better than n squared or an exponential or a factorial function, right? As you get up here, like you really don't want to do that, because that's going to take a lot more time. Okay, so I've got some examples for you. So if we are looking at a phone book, let's say we're looking at a phone book, and if we know so for constant time, that's analogous to if we know where we need to look. So if we know the page number and the name of the person, we can just flip to that page number, find the person. That's constant time. You're not looking through any of the names at all. A log n function is, let's say you know the name that you want to find the phone number for, and then you do binary search, which we talked a little bit about previously, which is where you start in the middle and you ask, is this person before or after the middle? And then if it's before, so let's say if we start in the middle, those are like the M's, and let's say our person has an L last name. So we'll go to the left and we'll pick the middle of that, and then we'll ask, is the person's name before or after this? If it's after, we'll throw away everything else and only look at the part where we need to. So binary search and in general, like dividing things by a number, it gives you logarithmic time. So one thing is that when you're working with logarithms, so if I'm dividing it by 2 every time, the logarithm is going to be base 2. If I'm dividing it by 4 every time, the logarithm is going to be base 4. Which, oh, I had that slide. Yeah, and so yeah, so you use a log when you're kind of dividing. The dividing operation determines how many steps your algorithm is going to take. So if you are like dividing the size of the input each time, you're going to get a logarithm for big O. Once you've decided like, oh, it's either log 2, that's the biggest term, or log 10, then you throw away the base and it's just log. So like log base 2 of n, the big O of that is just log n. Log base 10 of 10 is still, or of n is still big O of log n. Okay, so that's log. O of n is if I know a phone number and I want to find who it belongs to, and I'm going to check every name in my phone book until I find it. The worst case is that happens all the way at the last page. And so I would have made n comparisons if I have n names in my phone book. N log n is if we have some pages in random order and we want to put it into a new book, we can put it in the proper order in the new book. And so that ends up being like a binary search on that side, or a binary place. But we still have to go through each page of the phone book. And so that's why we have n multiplied by log n. For n squared, an example is, let's say we've got this stack of phone books, and let's say there's a typo in every person's name, and we have like whiteout and we want to go and fix that. So for every phone book, we need to go through every name and fix their name. And so that's n squared. N times n factorial, that's a little bit hard to think about. But an algorithm of that is called Bogosort. We'll get to that later. I'll talk about Bogosort later when we look at sorting algorithms. So I'll tell you what it is though. So Bogosort is a well-known terrible sorting algorithm where if you've got things in your list, first you shuffle them, then you check if it's sorted. If it's not sorted, you shuffle them again. And then you check if it's sorted. If it's not sorted, you shuffle and repeat until it's finally sorted. It's terrible. So one of your extra credit assignments, if you choose to accept it, is to write something worse than Bogosort. Okay, so let's see, what haven't I talked about? So the log base matters in determining the biggest term. Let me show you what I mean. So part of the worksheet today, I've got all of these equations where so these are like the steps that some algorithm takes. And I want you to find first what's the dominant term, and then what's the big O of that equation. So let's look at an example. So I'll tell you about this. So what's your initial thought? Turn to your neighbor and say, what do you think is the dominant term?
Yeah.
Like, which one is bigger? What's the biggest term?
Professor, can you zoom in? Thank you. Or this yeah, log 8.
All right, what do you think? Who votes for log 8? Who votes for log 2, log 2, log 2? Okay, so I think it's log 8. And I'm just gonna check my solution to make sure I'm not making this up. Where's my solution? Oh no. Here it is. Log 8. It's log 8. Because you go with the bigger base. So when you're comparing two logs, you go with the bigger base. And so to complete this one, you would say 3 log 8n. That's the dominant term. And then what's the big O?
Log n.
Great job. Yeah, so you ignore the 3, you ignore the base, and it's just log n. I have a whole worksheet. You can work on all of them. No, the worksheet is your active learning for today. I don't know where you got that. Okay. Let's see. Anything else I want to tell you about this? Okay, so when you're comparing two logs, you go with the bigger base. And then you throw it away when you're doing that. Okay, I think I might have gone through everything. So let me just walk you through the worksheet so you'll know what's expected of you. So I'm gonna put you. Do I want to put you in pairs? Yeah, I'll put you in pairs. And then can I have everybody listen while I explain the worksheet, please? Can I explain the worksheet, please? Okay, so I've given you a bunch of algorithms. Some of them are in Java, some of them aren't. But it should be fine. Like a for loop is a for loop in pretty much every language. Well, not some kinds of languages, but all the languages that I'm giving you. And so your job is to look at that and say, what's the operation? How many steps is it? What's the big O? And so I've given, that's the whole first page. And then the second page is a bunch more of these to say what's the dominant term and then what's the big O. And then I have two questions of, I've got an algorithm that is big O of n cubed. It takes 2 seconds to do this many inputs. How long does it take with this many inputs? So you'll have to bring out your algebra skills and get that done. All right, any questions? Okay, I'm going to okay, so what's the first one? Yeah, adding, so what's the big O?
N plus O n plus X. Plus O n.
Okay, okay. So yeah, so
Yeah.
yeah, so they're equivalent.
Yeah, it is.
Great. Okay, next group. Group 2. All right, do you have an answer for this one? No? Who does have an answer for this one?
I don't think anyone's. That's my guess. That's my bet.
Okay, right, because this one is tricky. Okay, so let's look at this one, this line.
Oh, I think I said the first. Unless you're calling.
I'm just concerned with the big O at this point. So let's look at this line. How many times does this line happen? So within
No.
this loop, it's going to happen. So it'll happen n, and then as I increases, it'll happen n minus 1, and then n minus 2, and then n minus 3. That's how many times this inner for loop happens. Or no. No, sorry, I'm wrong. That's how many times this line happens. And then, wait, no, sorry, I'm wrong. Sorry, I got confused. Okay, so let's. Okay. So let's say n is 5. So this inner loop will, and so if I is 0, then how many times does the inner loop happen?
5 times.
Yeah, so when I is 0, it happens 5 times. when I is 1, I is 3,
Five. No, because I was 5, it doesn't run 25 times. So, it's O n squared, or if it runs n squared times.
so when I is 1, it happens. Wait, is that right? Yeah, because it counts down to.
Wait, you actually had it.
Wait, no, I got the numbers wrong. This is supposed to be 2. This is supposed to be 3. This is supposed to be 4. Okay, now the numbers make sense. And so as I increases, the number of times we do this operation decreases, right? And so if we took away 5 and we had n, the number of times this executes in the entire function is n times, or n plus n minus 1 . So this is why it's a little different. So we've got n plus n minus 1 plus n minus 2. Yeah, I guess so. Yeah. But so the thing is, for this one, we know that this is an equation, right? This is a summation. And this evaluates to n times n minus 1 over 2. Right? Because we know, like, if you're summing numbers from 1 to n, that's n times n minus 1 over 2. If you're summing numbers from n down to 0, that's n times n minus 1 over 2. So that's the long version of how many times this thing executes. And so when we, like, boil it out, we get what? N squared over 2, or the whole thing over 2, minus n. And with that, we're throwing away the constants, we're throwing away the smaller term. And so our answer for this is big O of n squared.
Big O. I was asking how many steps? You didn't know that how big the city would be.
Okay, any questions on that one?
Questions asked, yeah, I don't know.
So this is, n squared. Okay. Let's look at the next one. So let a equals 0, I equals n. Log in. Why is it log n?
Binary search, that's what you told us. It gives half.
So it is, yeah. So the idea is that we're dividing, I changes, like we do the dividing of I by 2. That's what makes this similar to binary search. Where for binary search, we're dividing it in half every time, and we throw away the half we don't need. We divide it in half again. We divide it in half again until we get to where we're going. And so, because we're doing a similar dividing in half, it's a secret log base 2 of n, but for big O, we throw away the 2, and it's just log n. Okay, what about this one? The I times equals k. What's the answer to the I times equals k one?
Like what the big O is?
Yeah.
N to the K.
No.
Okay, K to the N?
No.
Is there any K involved? Yes.
Yeah, kind of.
You gonna help this? We were focused on 1 to 3. I'm gonna give it a shot. So, and it's 5. Actually, I'm gonna be honest, I don't know.
Does anyone else have this one? Yeah. So multiplication and remember multiplication and division go hand in hand, right? So because I controls the loop, and each time we multiply I by k. And so similarly here for where we are dividing I by 2 and we got log base 2, here we get log base k of n.
That's a good vision.
And so then when we're doing big O, we throw away the k, we get log n.
N squared.
Let me check that. Yeah.
Hey, hold on. Rising tide is Whoa.
Okay. Yeah, so this is constant, right? So this doesn't loop at all. So it's constant, we can throw it away, disregard it. But for this goes from 2 until n. And so this just ends up being O of n. Okay, did I scroll too fast? Okay, next group. Factorial? Yeah. Why?
Since it's just running through the equation once. With that last part.
Right, so once per number. So n minus 1, n minus 2, n minus 3, down to 1. And so since we calculate it, since we just do that calculation n times, then it's just n. Great. O of what? Okay, so not quite. So you are right in that we've got some division here happening. So there is a log. So this one happens log n. And then when we're looking at nested loops, so how many times does the outer loop happen? Yeah, and so when we've got this, we multiply. And so it ends up being n log n. Okay. Last one. Nobody got here? Okay. This one is easy, actually. This one is easy. So let's look at the inner for loop. How many times does the inner for loop happen? Can we bring the discussion back to algorithms, please? Can we bring the discussion back to algorithms, please?
I'm gonna try out this one.
How many?
Top one happens n times.
Great.
The inner one happens, also n times.
What about this one?
Happens n times as well.
So we've got,
N cubed. N squared plus n?
yeah. So because these two are at the same level, they're at the same level. And so this top one happens n times n times. So we've got n squared here for this nested loop, and then an n over here, which leads us to a big O of n squared. Great job.
I did that live, bro. What do you mean I did that? I did that. We live in the simulation.
Okay. So let's look at the expressions. Someone just call out to me, what's the dominant term for each one?
0.0.
Yeah. And so this is O of, what about the second one?
Yeah, more 10.
And so on this.
Okay, so the answer ends up being this, just because, and if you graph log n versus, or if you graph n log n versus n 1 point to the 1.5, n to the 1.5 is bigger. Okay, what about the third one? The third one.
And so 1.75.
Yeah, the third one.
Yeah. Make sure you got some.
And so then you throw away the 2.5.
Oh.
All right, someone else for the fourth one. The second one? Let me double check that. N squared log 2n. Yeah,
No, we didn't get it wrong.
yeah.
Can you explain why it would be the first one, second?
N is squared. N squared trumps n.
Oh, okay.
Okay, what about this one? Someone from this side of the room.
I think June wants to answer this one. What?
N log 3n plus n log 2n. Yeah, which gives us O of, sorry, n log n. Cool. All right, we did this one. What about this one? Someone else from this side of the room. (100n plus 0.01n squared. Who wins? Yeah. Because the n squared wins. So this is O of n squared. Okay, so then what about here, where it's reversed? N squared wins. All right, what about this one? N versus n to the 0.5 versus n to the 1.25. 1.25 wins. Great. All right, what about this one?
The first one. Oh, the first one. Yes, Professor. Thank you. I don't.
Because it both ends.
Let me check my answer.
Oh, you did right.
Okay, yeah, no, you're right. It's the second one.
Yeah.
That's right, I think.
Yeah, we got it. I was looking at it.
Yeah, I think if you graph this one, I think if you graph this one, that it shows that this guy's on top. Okay. Almost there. First one, n log n versus,
Thank you. Thank you.
yeah, n cubed, because n log n versus n cubed clearly wins. Okay, what about the last one?
Can you put University of Auckland?
What?
I said in 2020 is University of Auckland, Missouri.
Yeah, they were on the internet
Oh,
and they were useful.
how about-
That's where you won?
No. He's sorry, he's like a half a second.
Okay, which one's bigger? Log 4. Great job. Okay, 2 questions left, 1 minute left. What's 2,000 seconds? What about the second one?
16.
16. Cool. All right. Bring your worksheets in as you leave and make sure your name's on them, and then I'll give you points. Thanks for coming. I'll see you on Tuesday. Work on homework too.